Word. Now it's fine. So I think we did not miss anything much. Okay. Then the number of exponential number of stable matchings. Okay. So in this lecture, what we will look at is the structure of the set of all stable matchings. Okay. So let's say that M is the set of all stable matchings.
So I have a question. So when you say that there can be exponential number of stable matching, you mean in the case where M0 not equal to MZ, right?
Yes.
Yeah, because otherwise the stable matching is unique.
Yeah, exactly. So for a given instance, there can be exponential number of stable matchings. That I just want to say.
Okay.
And that exponential can be like 2 to the power n or something like that, like order of 2 to the power n.
So is it exactly 2 to the power n?
No. So there is an example of order 2 to the power n minus 1 that I know. And if you check some recent development, you can see some. I think there is one of order of c to the power n for any constants, for some constant c, that I know. But you have to look at some new papers. Okay.
Excuse me, sir.
Yeah. Hi.
Is this proof constructive that there are there can be exponential? Like, do they actually construct a preference list, or?
Yes, there is a construction. I think by Conway or someone. I have to check. I have not written his name.
Okay, but it's constructive.
It's constructive, and I can construct it on the next class.
Okay.
So set about stable matchings. So this is scripted M. Okay, I tried to write it, but I don't know how it look. So suppose this is the set of all stable matchings, and then we have last week we started it that stable match, all the stable matchings they constitute a lattice structure. Okay, so to prove it, it forms a lattice structure. So just first we need to define the partial order on M. So first we define a partial order on M. So I am not talking about I am not describing partial order or lattice. I think you know what does this mean. I mean the general definition. Okay, so suppose if M1 and M2 are two stable matchings, then we say M1 dominates M2 if and only if for each small m, for each man match his partner in M1 is better than, so for each m, let me write it in a different way. M prefers M1 to M2. Okay, or they.
So basically, you want to say M prefers M1, M2, M2 of M, right?
Yeah. Okay. Or they have the same partner. So you can say here that M1 and M2, which are not equal, suppose, which are.
So can we say that a man optimal matching dominates every other stable matching?
Exactly. So I mean, I will come to that later, but you can see that the man optimal matching will be the maximum point in the lattice, right?
So what do you mean by the maximum point in the lattice?
Like the upper bound of every.
Okay. I got it. So basically every means, so basically, yeah, every matching will be less than or equal to that man optimal matching.
Exactly. And women optimal matching will be worse than every matching.
Okay, so basically women optimal matching is a lower bound in the lattice structure.
Exactly.
And the man optimal matching is an upper bound on the lattice structure.
Exactly. Correct. You are correct. So for now, you know the so everybody understood what is the dominating means. So it means basically M1 dominates M2 if for each man that man M prefers basically M1 to M2 or they have the same partner. So they and if it happens, then we say that M1 dominates M2 and we denote it as this. So this is the notation that we are going to use. This just one moment. Just let me check if it is other way around or this way. That I confuse.
No, it should be the other way. M1 dominates M2.
Yeah. That's what I confuse a lot. So yeah. So this will be the other way around.
Also, can you just remind me what the partial order relation between two stable matchings is?
Yeah, that I will come just now.
Okay.
Okay. Oh, sorry. The partial order relation is here. I just said that. So basically.
Okay. The dominating. Okay.
That is the partial order.
Okay, I see.
If M dominates M1, M1 dominates M2, then that is the partial order. Okay. Now we have to prove that it is a lattice. So every two stable matching have like a common least upper bound and a greatest lower bound that we need to prove. So what is a least upper bound? It's also called join. So I'll just quickly go over the definition. So for two elements, suppose A and B, the join is basically A join B, and it is basically the least upper bound. It is the least upper bound of A and B. And what do we mean by least upper bound? Formally.
So basically here A and B are two stable matchings, right? When you're defining join.
So yeah, you can say stable matching, but for now I am defining it in general. So if A and B are two elements, and how can we define the join? So you can think that A and B are stable matchings also, and it will work. So what is the join? Join is basically there exists a matching C such that C is greater than equal to C dominates A. So in terms of stable matching, and C dominates B. And 2 is if D dominates A and D dominates B, then D dominates C. I think this is the definition of the join. Is it clear? Is the definition of join clear?
Yes.
Okay, so I think you can understand. You can say what is the definition of meet here. So A meet B will be like the opposite way around. Okay, so formally, so I'm not writing it anymore. So I think you can understand what is the definition of meet. It is the greatest lower bound or the infimum. Or infimum. Okay, so how we are going to define the join and meet in terms of stable matchings? So before we do that, we have a lemma. We say that okay, so before going to the lemma, first define the join and meet function for the stable matching. Okay, so M1 and M2 are two stable matchings, and how we are defining M1 join M2?
So I have a question. So the definition of meet will be analogous to the definition of join, right?
Yes.
Okay.
Shall I write it, or I think
No,
you
no,
can
no,
get
no.
it?
Fine, 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 fine. Fine.
Okay. So how we are going to define the join function for M1 and M2? I mean the join function in SM. Okay. So how are we going to define it? For each main, he chooses M1 of M if he prefers and M2 of M otherwise. So is it clear? What is the join function here? And for all W, C chooses M1 W if C prefers M2 W M2 over M1 and M2 W otherwise. Is the join and meet join function for in terms of stable matching clear? So what is happening here is, for each man he basically chooses his better partner among M1 and M2, and each woman chooses the worst partner among M1 and M2. Okay, and that will be the join function. So is it clear to everyone?
So I have a question. So once we define it for the men, so for every man chooses the better, why we need to define it for women separately?
So basically, for right now, we don't know if it will give us a matching or not. Okay, so we just defining it for each man and each woman, and after that we will prove that this is a matching. So we can always do that, right? We can choose. It can. I mean, for now it will not happen, I know, but for now it can happen that the better partner of two men is not. Sorry, better partner of each man. Suppose better partner of a man is for a man M is W, but the worst partner of W is not M.
Exactly, yeah.
So that's why for now we are defining it, but later we will show that this gives us a stable matching. Okay, I mean,
okay, but when you said that suppose there is a man M whose better partner is W, and but for W the worst partner is not M, then according to this definition, how can M1 join M2 be a matching after all?
M1 in that case, M1 join M2 cannot be a matching, but we are going to prove that this cannot happen in the next part.
Okay, since M1 and M2 are stable matchings, that's why.
No, not because of that. Yeah, that is the reason, but you have to prove it. I mean, this the thing that I just said right now. Okay, this will not give us a matching if we just consider a simple matching. Okay.
So basically, the situation you mentioned cannot arise. That will
cannot arise. That I am going to prove now.
Okay, fine. I got it.
Okay, so is it clear to everyone?
Excuse me, sir. So is it correct to say that after we have proved that the join function is a join function, like it's a matching, then condition A would actually imply condition B? Like the choice of the men will imply that women end up choosing this.
Yes, exactly. But we don't know right now, so that's why we have to define it for each man and each woman.
Yes, sir. Right. But eventually, like logically, it follows from the first condition.
Yeah. Actually, what we will do is we are going to use these two facts to prove that M1 join M2 is a stable matching.
Is a stable.
So it will be like a cyclic thing. Like we are using these two to prove that M1 join M2 is a stable matching, right?
Yes. So, but then logically, we should be able to only use condition A to prove the same thing. Is that correct?
Logic.
Because condition A determines the like it determines the matching.
Yeah. So what can happen is these two conditions can prove that M1 symmetric M1 join M2 is a stable matching. And also, if we have the proof already in hand, but no, I think we cannot do that, because to have the proof in hand, we need these two facts, right?
We need both. Okay.
Yeah. So we cannot, I mean, just have the proof, I mean, without these two facts, because we are using these two result to, I mean, these two statement in the proof.
Yes, but it's a little strange because condition A determines the graph.
Yes,
it determines the.
Yes. When you are doing when you are computing it, if you have the proof and if you just compute it with the best man for each best partner for each man, that will automatically give you the best worst partner for each woman. That is true.
Yes.
I think that's what you wanted to say, right?
Yeah, that it automatically follows. Yes.
Yes. Okay, so the meet function, I'm not writing it. I guess you can understand. Or anyone, do anyone want to tell me?
So basically for meet function, it will be sort of convert. So basically for every man will choose the worst and every woman will choose the best.
Exactly. Correct. So for everyone else, is it fine? I mean.
Yes, sir. And can we also say that the meet will automatically exist because let's say we take two elements and we want the greatest lower bound, we can just take the set of all lower bounds and take its supremum, which we know exists. So the meet function will exist, at least the existence we can prove from the existence of the join function and the existence of a minimum.
I think the existence of the meet function can be ascertained by the existence of the join function.
Yes, because we have a minimum already.
Exactly.
I have to check if, I mean, in a general case, if you just have the join function, then can, I mean,
yes, sir, because we can take the set of all lower bounds and then we can take the join of the set of that set of lower bounds, and that will be the, so we take two elements whose meet we want, and we just take the set of all lower bounds of those two elements, and we just take the join of that.
Can it happen like this? I'm not sure. I'm just guessing it. Like, okay, so suppose I have to thoroughly check it, but can there be a partial order that looks like this? Like this. So any two element has a I mean, the join function works here.
Yes, sir, but it doesn't have a minimum. We need a minimum.
Yeah. Okay, so you are saying if there is a minimum. Okay,
yes,
okay.
Because if there is no minimum, then we cannot ascertain that the set of lower bounds will be non-empty.
Yes. So basically, you are saying that by minimum, you already have a lower bound, and now you can just say that the greatest lower bound must exist. I mean, in the worst case, it will be the lower bound.
Yes, it will just be the supremum of all lower bounds.
Exactly.
But that can be situations where there can be other lower bounds, but this cannot be compared because this is a lattice. We cannot guarantee that all the elements can be compared, right? Like, so there can be minimum, there can be other elements, but
but the existence of the supremum means that there is a
but we need the greatest lower bound, right? So there can be elements, let's say A, B, C. Let's say C is the minimum. But then we cannot say that we cannot compare. We may not be able to compare A with B.
Yeah.
So
no, but the supremum of all lower bounds has to be the greatest. Greatest lower bound. No,
but the sup may not be still an infimum, right? If you just take a sup, it still may not be lower than the thing which you wanted to be lower than.
Okay, so will it not be a part? I think that then it will not be a partial order, right? But I think I will check it and I will tell you maybe in the next class. We are diverting a little bit.
Yes.
So it's better I will tell you in the next class. So maybe I can just write it down. So you want to say that join is there. We have join and minimum. Can do it automatically give the meet function. Okay. So this is the question, right? Okay, so we have the meet function now. Can you stop and start in like start again? I hope it's not a problem.
Yeah, we
Okay,
can
so
do it.
Yeah, I'm quitting it. Yeah. Admit participants. So I started recording and now I stop. So everybody joined now. Yeah. Someone late? Shubham.
I think Shubham is there.
Yeah. So now everybody is here. So we can start. So I started recording. Yeah, that is fine. Okay, so now we'll prove that M symmetric difference, M1 symmetric difference M2, not symmetric, join M2 is a stable matching. Okay, so first we prove M1 symmetric difference, join M2 is a matching. So how do we prove that? So I'm going to prove that if the partner of M is W, then the partner of W is also M. Okay, if we can prove it for every man, then it will basically give us that M1 join M2 is a matching. Is the proof direction correct? Yeah.
But I have a question here. So you should, if we can show that if M prefers W as a partner,
yeah,
then W will also prefer M. But it may happen that means two different men they choose the same woman.
Yeah, but then that woman can have to choose the both men, right?
Yeah.
I'm proving it in the I mean I'll prove it from the men's side, but you can easily prove it from the women's side also.
Okay.
So if the partner of M is W, so not if, so let's say that the partner of M is W if and only if partner of W is M. So you can prove it for if and only from the both side, but so that's what we are going to prove here. Okay, so first you let's say that for M, case 1, for M M to M is equal to W, then MW is belongs to right, and if this is to M1M is W and M2M is W, then from here also we can say that W equal to, right, and that means MW belongs to M1 join M2. Is the first part clear?
Yes.
Okay, so in the second case, so what we'll have, the partner of M is not the same in both matching. Suppose M1 of M is sorry, not M, W, and not prime. M2 of M is W prime. Okay, And without loss of generality, we can say that M1 of M join M2 of M is W. So W basically from here we can say that in the preference list of M, W comes before W prime, which is equal to M2 of M. Okay. Now if we notice the and now suppose we need to show that so this we need to show, right? M1 of W join M2 of W is M. So to prove it by contradiction, we want to say that suppose it is not true. To suppose the statement is not true. Now let's look at the preference list of W. What will be the preference list of W? So something will go and then M will come before, right? Because M1 because M cannot be after M2W. In that case, M will be chosen as the join, because for women we choose the worst one, and for M it will be, already we know that. So here we can see that in M2, M comma W will be a blocking pair. Contradiction.
So W is M1 of small m, right? Just to remember.
Yeah.
Okay. Fine.
Yes. So just to go back here. So yeah, W is the smaller, the partner of M in capital M1, and there is a partner of M in capital M2. We don't use that anymore. Okay. So and we say that W is the meet of W is the join of M1 and M2 of small m. Then W will come before M2 of M or W prime. Now we'll show that. To complete this proof, we need to show that M1 join M2 of small w is also n. Then it will be proven, our claim. So suppose it is not true, then M should come before M2 of W, right? Because if M comes after M2 of W in the preference list of W, then M1 join M2 of W will be M. So that's why, to prove the since we assume that it is not true, that's why M comes before M2W. And if it happens, then we can see that M and W basically prefers each other over their current partner, and that is a contradiction. Is it clear?
Yes. Now it's clear.
Okay, great. So for everyone it is fine, right? Okay, so now what is the next step for us? We prove that. I think Tejas, you sent me the proof, right? I have not checked it yet. I will check it today, but I think you
I sent the
this.
proof for the homework problem, which is a different thing. That man optimal is woman pessimal. I didn't.
Okay. Yeah. Sorry, I checked your mail, but I did not get time to check the proof yet. Okay, so I'll check it today. So M1. So what is the next thing we have to do? M1 join M2 is a stable matching. So we'll again prove it by contradiction. Okay. So what is the way to do it? Suppose there exists, which is a blocking pair. Suppose there exists M comma W, which is a blocking pair. To prove it by contradiction. Okay. So if it is a blocking pair, then without loss of generality, let's assume that the partner of W in M1 partner of W in M1 and M2, it is the joint function gives us M1 of W. Okay, so we can assume that without loss of generality. And then if we look at the preference list of W, so can anyone tell me how will it look like?
M2W must come before M1W.
Yeah, so basically small m must come before M1W, and which is basically is equal to, if I write it on the top, right? And how would the preference list of M look like? So W comes first because MW is a blocking pair, and after that, what shall come?
Wait, sorry, I have one question.
Yeah.
Small m is M1W, right?
No. It's a different proof now.
Okay, sorry. So you said that is a blocking pair in M, right? In the
Yes.
stable, in the matching.
So it's a blocking pair in this M1 join M2.
Yes, which means M is matched with
Someone
W.
else.
So, and you're assuming that M1W join M2W is equal to M1.
I think you're okay. So we use the same notation. That's why I think it's confusing. So let's say it is M star W star. Okay.
Okay.
That's an edge. That's not a matching. So M star W star is a.
Oh, okay. Okay, sorry. Yeah, okay. Now it's clear. Sorry.
No worries, it's fine. So I think it's clear right now, right? So M star W star is a blocking pair in M1 join M2. Okay. So now I'm going to prove that M star W star is also a blocking pair in M1. That my goal is to prove that. Okay. So I'm checking that without loss of generality, I'm assuming that the partner of W star in both M1 and M2 comes from M1. Okay. That means the W star basically prefers M2 over M1, right? So now if I write the preference list of W star, then M star will come first, and after that this M1 W star will come. And if I write the preference list of M star, what does M star do? M star basically chooses the better partner between M1 and M2. And since M star and W star is a blocking pair, so W star will come before M1 of M star or M2 of M star. Okay, and then the other one will come. You can understand what do I mean by the other one? It's the other one from M1 and M2. Okay, so here we can see that and which is a contradiction. So is the proof clear, or do you want me to?
I mean, you assume that M star W star is a blocking pair in M, right? Oh, sorry, in M1. Okay, I see. Okay, sorry.
No.
Yeah. Now it's clear.
I did not assume that is a blocking pair in M1. I assumed M star
Yeah,
W
sorry,
star is a blocking pair in M1 join M2.
Yeah. Now it's clear. Yes, sorry. I just read M instead of M.
Sir, I have a question.
Yeah.
So if we go to the definition of join M1 join M2, and
Yeah.
so as we were saying that in the definition of M1 join M2, the choice of the yes sir.
Yeah.
Yes sir. So here as we were saying that here we were saying that the choice of the men should be logically enough, and so I was saying that we will not need the choice of the women to determine the join. And I think, sir, I can prove it. I think I'm able to prove that if you just decide what the men should do to construct M1 join M2, then you will get a matching. Like, you do not need this. This will be forced from this first. I think I'm able to prove it if you can listen to the.
Okay.
If I can say my okay. So let's say that we have two matchings, M and M prime. Okay, and let's say that M1 is matched to W1 in M, and M2 is matched to W2. Okay, and let's say in M prime, M1 is matched to W1 prime, and M2 is matched to W1. Okay, so let's say that the join is not. Let's say that the join is not a matching. So that let's assume that in the join, M1 and M2 both end up joined to W1. For the sake of contradiction. Now, if M1 and M2, so we'll show that this cannot happen only by using what men do and not giving any prescription to the women. So if M1 and M2 both end up joined to W1, it means that it means that W1 is in the preference list of M1, and M1 is matched to W1 in M, and in M prime, M2 is matched to W1. Okay, so in M, M1 is matched to W1, and in M prime, M2 is matched to W1. Obviously, M2 cannot be matched to W1 in M only, so we have to assume that it's in the other. So that's what I'm assuming. M2 is matched to W1. Okay, now we can set up now we can see now M implies that the preference list. Okay, now because M1 and M2 are both matched to W1 in the join, it means that in the preference list of M1, W1 is higher than W1 prime, and in the preference list of M2 also, W1 is higher than W2. So okay, so this is the situation. Okay,
so you want to say there is a blocking pair or something?
Yes. So yeah, by assuming that M and M prime are both stable matchings already, we can actually more than that, I'm proving that we can actually determine the preference list of W1 and W2. So I can prove that in W1, M1 has to be higher than M1 has to be higher than M2. Okay, if M has to be a stable matching, M1 has to be higher than M2. Otherwise, because if M1 has to be higher than M2 for W1. Because already for M2 W1 is higher, and if M2 is higher for W1, then that will be a blocking pair in M. So that's why we've determined the preference of W1. Similarly, we can now show that for W2, for the preferences of W2, it has to be the other way. Otherwise, M prime will have a blocking pair M1 W1.
Okay, so I have some doubt over this part where the blocking pair basically needs the both sides, right?
Yes, sir. So what is the question?
Okay, I don't have any concrete question right now, but
okay, can I write this and send it to you? Maybe then.
Yeah, that will be great. I mean, I was thinking to ask you that.
Yes, I'll just write it after the class and send.
Yeah, it will be great if you can write me and write it and send it to me. Then I can just thoroughly check it.
Yes, sir. Yes, sure.
I hope it will be good. Okay, thanks. Okay, so if we come back here, so is the proof clear here for you?
Yes.
And everyone else. So why it is a stable matching? Okay, so if it is clear, then we already know that. I mean, analogously, we can prove that is a stable matching. So I'm not proving it. So M1 meet M2 is also a stable matching. I think it will also be analogous proof. Okay. So lemma. Now control D. Now from these two proofs we can say that other way around. And the maximum, so from here now we can say that it is a lattice with the join and the meet function defined above. So I think it is clear, right?
That written m comma within first bracket.
That is the list precedes. That's
Okay. Yeah. Fine.
Sorry, the thing is not so good. Okay, so I'll try to write it. Just one moment. It's hard to write in this. Okay, now it is better, I guess. Okay. So you can see white is a lattice now. For each two elements, we have a minimum upper, least upper bound and greatest lower bound, which is basically their meet function and the join function. And the next thing is you can also check that. Oh, sorry, the other way around. Is also a distributive lattice. Okay, so I'm not going in much details of this because I will go to rotation after this. Okay, so one thing is that the maximum element here is a man optimal matching that we have just said, and the minimum element here is the women optimal matching. And what is a problem in this structure? So one thing we know that the number of stable matching of a given instance can be exponential given an instance. So the size of this scripted M that can have the exponential size. So that means any algorithm that basically generates this lattice structure requires an exponential time. So we need something that needs a polynomial time and polynomial space to represent all the matchings in scripted M. So for that, we are going to use rotation poset. So is the motivation behind rotation poset clear? Because this lattice can have like an exponential size. So we can directly use this lattice structure to prove some algorithm, right? That's why we are going to use this rotation poset, which is like have like polynomial space, which takes a polynomial space to define all the stable matches. Okay, so before we go to rotation poset, we need to first define rotation. What is a rotation? Okay, so for that, let's first do some notations. So suppose M is the stable matching. Case M, this is important, okay. First woman on M's list after his partner in M who prefers M over her current partner. So what do I mean by that? Is that suppose M is there and his partner is W, suppose, and suppose W prime is the partner just after M. So in the preference list of M, we have W, and then we have some, and then we have W prime, and anyone in between W and W prime basically prefers their own partner over M. So W prime is the first partner who basically prefers. So suppose this is the partner of W prime. So W prime is the first woman after W who prefers M over her current partner, and M basically prefers, of course, W over W prime because W comes before W prime. In that case, W prime will be called as subscript of capital M of small m. So is the definition clear? What is SM of M means? Because this will be needed actually for our to define rotation. Okay, so if it is clear, then we can define a rotation. So a rotation basically, rho is basically is equal to some pair of men and women such that Mi Wi are all matched and Wi plus 1 is equal to Sm of Mi for all I. And I basically, it is like a cyclic order. So for r minus 1, it comes to 0. Okay. When I equal to r minus 1, then I plus 1 basically becomes 0. Okay. So is the definition of rotation clear to everyone? Hello?
Yeah, I think it's clear.
Okay, so for others. So if I draw a picture of rotation, if it is not clear, then I'll draw a picture of the rotation, how it will look like. Okay, suppose there are this row contains four pair of men and women. So it looks like this. Suppose first is M0, W0, then M1, W1. These are 4 matched pairs. M3, W3. So M1 is the W1 basically SM of M0. Similarly, W2 is the SM of M1. W3 is the SM of M2, and similarly W0 is the SM of M3. So this means here M0 basically prefers W0 to W1, but W1 prefers M0 to her current partner M1. And in similar way, we can complete the preference.
So can we create a rotation from any matching by a permutation?
From any matching, I mean, so basically in any stable matching, if it is not a Wien optimal matching, then there will exist at least one rotation.
Yes, so that's what I'm okay. So like we can permute the MIs and we can create.
Yeah.
Okay.
You can continue. You can start with any man M, and you can continue until you reach the same man again. And if you don't reach that man, I mean the same man, you start from M0, and if you don't reach M0 again, then you start from any other vertex. Okay. Eventually, you will find at least one rotation. I mean, if it is not a Wien optimal, there will exist at least one rotation. Okay. So now, is the definition of rotation clear? So basically, say it again. Suppose you are given a stable matching M, and SM of M is basically the first woman in the preference list of M after his current partner who prefers M over her current partner. The first woman of M's list, after M of M's current partner, who prefers M over her current partner. If it happens, then that W prime will be called Sm of M. And there is a picture of it. I mean, what do I mean by that? And a rotation is basically a sequence of couples who are currently matched, such that the property that I just said holds for every Wi. Okay, so if it happens, then it is a rotation.
So essentially, if in this case, for example, if M0 and W0 were not to be matched, then M0 and W1 would form a blocking pair, correct?
No. Why would M1 and W1 will?
M0 and W1 would form a blocking pair if, let's say, W0 were to break it off with M0.
Okay, yeah.
Because
so basically what I'm going to say here is, if we remove all the matchings Mi Wi and match Mi and Wi plus 1, then it will also be a stable matching. If we remove for all I and match for all I, then the matching is stable. I think you can see why it is stable. Because the only pairs now who can create a blocking pair are Mi Wi's, but they cannot create a blocking pair because all the Wi's preferred their current partner over the unmatched edge, right?
Right, sir. But if only W0 leaves M0, then that does not imply that M0 W1 will be a blocking pair, because there are things in between W0 and M and W1.
Yeah, but
they don't prefer.
Yeah, so that's why I said here.
But M1 also does not prefer W1.
M1 also doesn't prefer W1.
Like suppose if W0 breaks it with M0 and goes to someone else, but that doesn't mean that M0 W1 will be a blocking pair, because there may be some woman in between W0 and W1 for M0 whom he can pair with.
None of those women prefer M0. The ones between.
So for M,
W0 and W1.
So but it is also not true that M0 prefers W1 to them. So for blocking pair, it has to be both ways.
Yeah, so here I'm saying that if you remove all the edges Mi Wi from the matching, and if you match,
yeah, then it is clear. If you remove all, if we change all of them, but one of them will not be enough.
No, one of them will not be enough. You have to remove all of them, and if you match, you have to match all of them. If you remove only one of them, then it will not be a stable matching, because the size will differ. It will not be a perfect matching anymore.
Yes.
Because you need to remove at least 2 edge from here to add a new edge. Okay, so so what is happening here in the preference list of M, W is his current partner. Suppose W0, let's say M0, and W1 is the first partner who prefers M0. So when M0 is matched with W1, neither W0 can block M0 W1, or these ones can the women in between W0 and W1 blocks M0 W1, because they prefer their own partner over M0. So none of the partners here, none of the women here in the list of preference list of M0 blocks M0 W1, right? So that's why.
Sorry, can you just repeat why So I understood why the women between W0 and W1 cannot block, because they don't prefer M0. But what about W0?
W0 basically prefers her current partner over M0, right? What is the after we make the switch? What is the partner of W0? It is M3.
M3, yeah.
And W0 prefers M3, her matched partner over M0. So that's why.
So how do we know? Okay, That's okay. I see. Okay, that's the definition. Okay, I see.
Yeah, that's the definition. And anything before W0 cannot block M0W1. Otherwise, it will also block M0W0. So anything over here cannot block M0W1, right?
Yes, correct. Yeah.
Otherwise, it will also block M0W0.
Yeah, but M0W0 was not being blocked. Okay.
Yeah, exactly.
Okay.
So is the definition of rotation clear? Because this is like quite important for the structure of stable matching. So if you have any other doubt, please tell me.
So we can use a rotation to go from one stable matching to another.
Yes.
Okay, sir, but even if we define rotation as to not use all the vertices, and like if we have a cycle in between, which is of this kind, then also we can use it to go from one matching to another.
Yeah, so this cycle doesn't contain this cycle may not contain all the members, right? All the men or women.
Okay. Oh, it doesn't have to. Okay.
Yeah, it's just a cycle that you start with. So basically, what you did, you started from. So how do you find a rotation? So you start from M0, and you see that W0 is your partner, and W1 is the first woman who prefers M0 over her current partner. So we come to W1, and we see that M1 is his current partner. Okay, so we go to M1. And we check M1, W1 is his current partner, and W2 is the first woman in the list of M1 who prefers M1 over her current partner. And in this way we continue. And finally, suppose we come to W3. Here, the partner of W3 is M3, and in the preference list of M3, W0 is the first woman who prefers M3 over W3. So W3 is W0 is the first woman in the preference list of M3 who prefers her current partner M0 over M3. Okay, so here we can see that after we go to W0, we see that her current partner is M0. So here we can see that we have already created a cycle, and then we say that it is a rotation.
So W0 was defined to be M0's current partner.
Yes, so that's why here from this
how
line.
do we know that? So with M3, when we go to M3, how do we know like it goes back to W0?
So even if it doesn't go back to W0, if it goes to W1, then also we can take it as a rotation. We can just remove M0 and W0 from the picture.
Exactly. Sorry. Then okay. Yeah.
So it doesn't have to be a cycle.
So it can go anywhere in the middle. Okay.
Yeah.
It's like a graph. Yeah, we have to cycle.
Okay. So it can look like this. So suppose this is a path, and after some time, the path
we just
will
come back at some point of time. Okay.
Some point, and then we just can just ignore the first.
Yeah. Okay. Yes. Yeah.
So that is the thing. Oh, sorry. Did I erase something? I think no. Oh, no, I did not erase anything. Okay, so this is the definition of rotation. I think it is clear, right? To everyone?
Yes.
So it can be that a matching may not have a rotation, right?
So you can prove that if a matching is a women optimal matching, then it doesn't have any rotation. But if it is not women optimal, then there is at least one rotation.
Okay.
And you can find that rotation by taking the symmetric difference with MZ and the women optimal and that other matching, and then modifying a little bit, then you can find the rotation. Okay. Okay. So the rotation part is clear. And if suppose this structure is already present in the graph, then we call this the rotation is exposed in that particular graph. Okay. So if we can find such a structure, I mean, in the current matching, current graph, then we say that this rotation is exposed. So we'll come to this later. And by eliminating the rotation, we mean that we remove all the MIWIs and we match all MIWI plus 1. That is called eliminating the rotation. The rotation. Okay. So after this, let's look at an example. Okay. And after that, in that example, we can see what are the rotations and what we do with the rotation. Okay. So I'll just stop the meeting again, sorry, and I'll come back again. By Thursday, I think it will be clear, fine. Okay, bye. Please remind me every time. Okay. So in the preference list of M1.
Sorry, I just have one question. So why is the
yeah.
list incomplete here?
Okay, so I'll come to that. I mean,
Okay.
for now, you can say that you can think that their lists are not incomplete, but the women who are not present in the list are like arbitrarily ordered after the current one.
Fine.
Okay, so for now, you can think like that.
Yeah.
I'll come to the incomplete list later. Maybe not today, but in the next class. Okay, so for M1, suppose W1 is his current partner, and for W3, you can see that W3 prefers. Okay, so what is the main of? So let me take a screenshot. Okay, so it will be better, I think, to write down. Print screen. Just one moment. Control V. So that I can write it right on the top of this. Control X. Control V. So I just brought it here because I can write on top of this now. Okay. Okay. Now I think this is visible. Is the journal page visible? Can you?
Yes.
Okay. So what is the rotation here? Rho 1. Rho 1 is equal to M1 W1 and M2 W2. Okay. Arvind is here.
Sorry, so you start at M1, but the matching, wait, it's a rotation with respect to which matching?
With respect to this M1, this matching.
Okay. So M1 is currently matched to W1. So why is M1 W1 a rotation?
So if I go back to the definition of rotation here,
W2 prefers M1.
Okay, I see.
MI WIs are all matched in the current matching.
Okay, I see. Yeah.
Okay, so if I come back here again, M1 W1 and M2 W2 are the rotation. So I write here M1 W1, M2 W2. Okay, so let's see here. So M1 is currently matched with W1, and if I go to W3's list, W3 basically prefers M3 over M1. So we cannot use W3. Next we come to W2, and we can see that W2 prefers M1 over M2. That's why we have the rotation M1 W1 W2, and W2 prefers M1 over her current partner, which is M2. Plus, and M2 basically prefers, you can see M2 prefers W2 over W1. So, okay, no, not this way. M2's partner is W2. Now, if we check the preference list of M2, W1 is his next best partner, next best choice, and in the preference list of W1 basically prefers M2 over M1. So, from W2 we add an H to W1, and now we can see that we have completed a cycle. In that cycle, W1 basically prefers M2 over M1, M1 prefers W1 over W2, and W2 prefers M1 over M2. So is the rotation clear here? Why M1 W1 and M2 W2 are rotation?
Yes, now it's clear.
Okay, so in this way, and there is more rotations also. Like there is another rotation, that is the next rotation is. Let me just go over here. Row 2 is M2 W1 and M3 W3. The second one is, suppose this is row 2, M2 W3, M2 W1, M3 W3, M2 W1, So here in the second rotation, we can see that the second rotation is not exposed yet in the graph because W1 is not the best partner of M2 yet in this graph, right? So it is not satisfying all the conditions. So that's why this rotation, we don't say that, we say that it is not exposed here, but we say that this rotation is exposed in the current graph. Okay. And what do we mean by eliminating this rotation rho 1? What we do is we remove this edge. So basically from the graph, we remove W1 and W2, M2 W2. So M1 W1 and M2 W2. We remove these edges and we match the other edges, that Mi Wi plus 1. Here it will be M2 W3 and no, sorry, not M2 W3. M2 W2 and M1 W2 and M2 W1, and rest of them are matched with their current partner. M1 W2. So here it will be M1 W2, M2 W1, M3 W3, M4 W4. So is there elimination of rotation clear, or do you want me to repeat it?
So after eliminating the first rotation, this second rotation becomes exposed. Is that correct?
So, yeah, exactly. So after we remove this first rotation, now if we see that W1 is the best choice of M2 because we have removed them. W1 is the best choice of M2. And if I go to the M2's list, we can see that if we go to W3, W3 prefers M2 over M3, which is his current partner. That's why we can have an edge like this, M2 W1 and W3. W3 prefers
and W3 is matched to M3,
but she prefers M2 over M3 here. Now if I go to W3 is matched to M3, and in the preference list of M3 we can see that after W3 we have W1, but in the preference list of W1
prefers M3.
Prefers M3. Just one moment.
Yeah, W1 prefers M3 to M2, so we can complete the cycle.
Yeah, W3 prefers M3 to M2. Sorry,
prefers M3 to M2.
W1 prefers M3 to M2, so we can complete the cycle. Yeah, and
can you just repeat the definition of exposed?
So a rotation is exposed if it satisfies these conditions, that for every Mi, Wi is his first choice, best choice, and the Wi plus 1 is the first choice after Wi, who prefers Mi over her current partner.
So it's the same thing as a rotation. I mean, what's the difference between the rotation and an exposed rotation?
In the exposed rotation, we have
so the edges of the rotation should be there in the current matching.
Yeah, so yeah, that is one thing. The second thing is that the partner in the current matching should be his best choice. This best choice and second best choice, that should hold.
For best, okay. So the difference between the rotation and exposed is that the Mi. So what do you mean best choice as per?
Sorry, no, not the best choice. Sorry, this is correct. That the rotation is exposed if all the edges, the Mi Wi's are matched currently.
Mi W are matched current. Okay.
Yeah.
So any rotation where Mi W is matched is an exposed rotation.
Yeah, all the Mi Wi's are matched at that moment.
So that is the only condition.
Yeah, only condition. Okay. Mi and Wi are matched, and the rotation condition is like that we have that the first woman who prefers MI over her current partner. That is the condition of the rotation. Okay. Okay. So first we have seen that row 1 was exposed because the first matching was M1W1, M2W2, M3W3, M4W4, M5W5. At that time, row 2 was not exposed because M2W1 was not matched.
Yes.
So in this way, so when we eliminate the rotation row 1, then we see that the rotation row 2 is exposed. Okay, so then we can make a poset from here. How? That we can say that row 1 basically precedes row 2. Row 1 precedes row 2. If row 2 is exposed when we eliminate row 1. So is it clear? So in this way, we can make a partial order among all the. So basically, if we say that R is the set of all rotations, then in this way we can basically make a make a partial order among all the rotations.
So this is with respect to some matching which we fixed before, and then we have this partial order.
Okay,
the rotation doesn't depend on matching, does it?
Yeah, no. The rotation doesn't depend on matching. So basically,
no, but being exposed depends on the matching, right? I mean, if you don't have matching, you don't know what exposed is.
So basically, we start. One thing you can prove that this set R, the rotations in the set R, doesn't depend on the only depends on the instance. Not on the matching. And
yes, sir, but being exposed will depend on the matching. So how is it well defined? Or yeah.
I mean, I don't get. Yeah, even I don't get the same point.
Or maybe it should be for all. So in any matching, whenever row 2 is exposed, then is exposed when we eliminate row 1 for any matching. Is that true? Like that should be the condition.
Yeah. Sorry, can you repeat it once?
Yes, sir. So my question is that is this so this condition of precedes, does it mean that for in any matching, whenever row 1 is eliminated, row 2 will be exposed? If this happens for any matching, then we will say that row 1 precedes row 2.
Yes. So basically, when you are given the instance, and if you eliminate row 1, after that row 2 can be exposed. I mean, row 2 is not exposed until row 1 is eliminated.
Yes, sir, but it might, sir. But can it happen that for some matchings, eliminating row 1 will expose row 2, but for some matchings, eliminating row 1 will not expose row 2?
No. This will not happen because so basically what we are doing, we are starting from the main optimal matching. Okay, so I think I missed some line. Okay, so we are starting from the main optimal matching, and we are going towards the even optimal matching. And when we eliminate a rotation, basically eliminate the rotation row 1 in. So if row 1 is present exposed in main optimal matching, then or in any matching that we are coming from that we got after exposing some eliminating some rotation from the main optimal matching, and row 1 is exposed in that matching, then if we eliminate the row 1 rotation there, then we will get the row 2 rotation exposed, otherwise not. Okay, so I think I confused you a little bit.
So you can just repeat it.
Yeah, so suppose we basically we start from the main optimal matching, and after suppose we have eliminated some rotations, then row 1 the rotation row 1 is exposed. Okay, so now we say that until we remove the rotation row 1, then till that time the rotation row 2 will not be exposed. Is it
so
clear now?
that is the definition. Okay.
Yeah.
Okay.
Until we eliminate row 1, the row 2 will not be exposed.
So that doesn't mean that if row 1 is eliminated, row 2 will be exposed.
No.
So then we should maybe change the definition. I don't know. Like
Ah,
row
okay,
2
okay.
is not exposed if row 1 is not eliminated. Maybe I don't know.
Yeah. Thanks. The writing is not correct. The row 2 is not exposed until. I think now it is correct, right?
Yeah, now it's I think correct to what you said. Yes.
Yeah. Okay. So yeah. So in this way, basically, we define the partial order between the rotations, and if R is the set of all rotations, then, and one more thing we can see that the rotations, if we take any two rotations,
But I mean,
row 1 and
but sorry, I have one question. So
Yeah.
as we keep eliminating rotations, the matching changes, right? The underlying matching changes.
yes.
So this order will depend on some order of exposing them, because
Yeah.
if we change the order in exposing them, then we'll have something different, because at each stage,
Yes.
I mean, okay, because one more question is, even each rotation, it uses the meaning of current partner. So the current partner is with respect to the current matching, correct?
Mhm.
We have, okay, so all this depends on which order we are exposing it in.
Yeah, but
fine.
I'm saying it is just the set of all rotations. It's not like any ordered set of rotation.
Yeah,
So just the set of all rotations.
Yeah.
I'm saying that set is not depending on the matchings. That just depends on the instance.
So, but even this partial order should not depend on any matching.
The partial,
So-
yeah. No, just one moment. Yeah, partial order doesn't
It should
depend on
not
the matching.
theoretically. Yeah.
Yes. So this R set of the rotations, they don't depend on the matching, but they just depend on the instance.
Sir, and can we say that whenever we expose and eliminate a rotation, whenever we eliminate a rotation, we go down in the lattice of matchings?
Yes, exactly.
Okay.
So, and one more thing is that if you take two rotations, row 1 and row 2, just one moment. Either they are totally disjoint or they are identical. I mean, either they are totally edge disjoint or they are identical.
Sorry, I don't understand how the set R is independent of the instance, because when we define the rotation row, we talk about the fact that a woman, so I mean, okay, in a man's list, the woman is the next one on his list who prefers the man over her current partner.
Yeah.
So when you say the current partner is with respect to some matching, correct? So then the whole rotation would depend on what matching we are considering, because the current partner would depend on when the matching changes.
So,
Yeah,
but
that
if
is-
there is some matching,
I mean, for example, if you have a woman optimal matching, then you wouldn't have any rotations R to begin with. Whereas if you have a man optimal, then you will have some rotations.
Oh yeah,
So-
but I'm just saying that the set of rotations R means all the rotations that you can that can be exposed given an instance. I'm not saying R is all the rotations of a particular matching.
sir, or is R the set of all rotations when we run over all possible matchings?
Yes, for a given instance, for a given instance.
For a given
run
set.
over all the matchings, then all the possible rotations which can get is in set R, correct? That's
Yes. Yeah. Set of all rotations.
Okay, it's all rotations for all possible matchings. Okay.
All possible matchings. Of all possible matchings.
Okay. Now it makes sense. Okay.
So I'll prove why it doesn't depend on the instance in the next class. Okay, it's 25. So can you go for like 5-10 minutes?
Yeah, fine.
Is it
Yes.
fine?
Yeah.
Okay. So then I can complete this rotation part, and then we can start from the new Okay, so this R is basically the set of all rotations that you can get from all the all the rotations that you can obtain, and then we can say that this R comma this precedence, it forms a partial order. Or poset. Okay, so Control D. And we say that, and there is a theorem. So do you know what is a closed subset mean?
In topology or?
Not in topology, sorry. In order theory. So basically, if you have some, suppose some like this, some partial order,
then everything below should also be there, or something like that.
Yeah. So if this element is there, everything above.
Oh, above.
This should be there. So if this is there, this should be there. This should be there. This should be there, and this should also be there. Others may not be there. So that is like a closed subset of this set. Okay. So theorem, there is a theorem that says that there is a bijection between the set of all stable matchings and the set of all closed subsets of R comma. Okay, so I'm saying that there is a bijection between all the stable matching, the set of all stable matchings, and the set of all closed subsets of R. So why I'm saying that, suppose R prime is a closed subset of R, then what we do is, if we eliminate all the rotations in R prime, then we are going to get a stable matching. I mean, if M naught is the main optimal matching, and we remove all the rotations of R prime, so can anyone say why can we remove all the rotations of R prime from M naught? I mean, why all the rotations will be exposed at least I mean sometime. I mean, it may happen that some rotation of R prime may not get exposed at all. But I'm saying that the rotations of R prime will get exposed sometime, like after we remove some other rotation of R prime, all the rotations will eventually get exposed. Can anyone say why it is true? Okay, this is true because we are taking a closed subset of R. R prime is basically a closed subset of R. That means if a rotation is present there in R prime, then all the rotations that precedes it, who has to be exposed before this particular rotation is exposed, are also present in R prime. That is that's why we took a closed subset of R. R prime as a closed subset of R. Okay, so that's why after we can eliminate all the rotations of R prime one after another and in an order, and then we get a stable matching. And the other way, for the other way around, we can say that, so we can have some lemmas, small lemmas. So one thing we can say is, if there are like two consecutive stable matchings in, if in the lattice structure that we have seen before, then their symmetric difference will be a rotation. That you can try to see, I mean, why it is true. But the sketch is basically the sketch is basically if those two are the symmetric difference is not a rotation, then you can find another matching in between those two matchings, and that will be the idea. So you can try to complete this proof.
So is it a rotation in the first stable matching or the second stable matching? When you mean two consecutive ones?
In the first one. So basically,
okay.
if I'm saying like if there is like two matchings, M1 and M2. Okay, and if they are consecutive in the lattice structure, then yeah, M1 symmetric. That's a good point. M1 symmetric difference M2 has a rotation. Is a rotation in M1. Rotation.
M1 is a bigger one, right? M1 is the one above M2. Okay.
Above M2, exposed in M1, and if we eliminate M1, oh sorry, if we eliminate the rotation, we get M. So you can try to prove why it is true. The main that you can try to approach in this way, that if it is not a rotation, then there will exist another matching in between M1 and M2. Okay, and that way you can try to prove it. Okay, so if we go back to the next part, so using this lemma, we can prove our prove the claim that here that every stable matching is a closed subset of. So we have first we have proved that. So we have proved in this way. So if there is a closed subset, then there exists a stable matching. Now we will prove that every stable matching is a closed subset of. For every stable matching, there is a closed subset of R. Okay. So let's take the main optimal matching and find any path to M in this scripted M lattice. Okay, we take all the rotations that come along this path, and if we take all these sets, suppose this is row 1, row 2, row 3, and row 4. Row 1, row 2, row 3, and row 4, and this R prime will be a closed subset of R. This R prime is a so you can try to also prove this one. So this is like the second problem. The first one is here. Okay. Okay, so here what I am saying is that if M0 is the main optimal matching and M is some other matching, then suppose row 1 is the, and suppose there is a since it is a lattice, that means there is a path from M0 to M in this structure, and in this structure, let's say that for every edge we have the rotation row. For the first edge, the row 1 rotation is exposed, and after eliminating we get this matching, and here we eliminate row 2 rotation and we get this matching, and after we eliminate row 3 we get this matching, and after we eliminate row 4 we get the matching M. Then we said then I'm claiming that this row 1, row 2, row 3, and row 4, it is a closed subset of R. And I think it is obvious to see why it is a closed subset of R. And if we remove this, that means for this matching M, we got a corresponding closed subset, that is row 1, row 2, row 3, and row 4. So I think it is clear, right? I think then the one thing you can do here is you can try to. I will send you a lecture note. You can go over it. So it will have this mainly these proofs. And if you have some doubt, then you can just tell me, and I can you can explain that part. Is it fine?
Yes.
Yeah. So you will send the lecture notes to us, right? Okay.
Yeah. So I'll send this class note, and I'll send the lecture note, the part that is relevant for us.
Okay.
And you can have a go over it, and you can tell me if you have some doubt. Then we can also meet during the weekend also again. Or in the next.
Sir, it will contain everything, like everything taught in this class, like all the lattice also.
Yeah, it will contain basically. So I'll send you this lecture note. I'll just show it to you also now. Just one moment. Where is it? So it's visible right now, right? So here you can see that. I'll just go to the first page. Yeah. So the structure of I'll split this part of the. I'll send you the whole thing and also the part like 2.2.3. So here you will see that rotation poset. First of all, you will see the stable. Sorry. First, you will see the lattice structure of the stable matchings, and then you will see the rotation poset. And after that, here the rotation poset is defined, and just one moment. Mobile is. Yeah. So after here you will see the definition of rotation, and after that you will see an example of rotation. Here the example with all the stable matchings and all the rotations. And here you will see the lattice structure on the left, and on the right you will see the rotation poset and all the rotations. So you can go over this example, and I'll suggest to have this particular example and try to compute all the stable matchings from scratch. Like you know how to compute the main optimal matching, and after that you find the first rotation, and then find the second matching, and then find the second rotation, and find the third matching. And in this way you can compute all this. You can verify all these stable matchings and all the rotations. And here you can see that by this structure we mean that the row 1 has to be eliminated before the row 2 is exposed, and row 3 and row 4 are exposed when we eliminate row 2. So row 3 and row 4 doesn't depend on each other to be exposed. So row 3 and row 4 both get exposed when we eliminate row 2. So that's why we have this structure. And yeah, so that's it. Yeah, that's the main part of that's what you have in this. So I'll send you this link.
So it is to section 2.2, right? From that.
Yeah, section 2.2.3, I guess. So you go over it, and if you have any doubt, you can just write me, and I will try to explain it one more time.
Okay.
Okay. Okay. So thank you. So we stop it for today.
Yeah.
Okay. Bye.
Thanks. Bye.